we'll go from there. All righty. So I'll share my screen. That would help. Just had a stiff neck today too. I know I look funny in the. I can't turn my head very well in the video here. So with that being said, which is totally irrelevant, let me show you where we're headed here today. So right, can't believe it's week 8, and by the time I get to Friday, I'm already in a tizzy having all the other classes and stuff. But we're halfway there, man, and we're halfway through the semester. You guys are hanging in there. We've got all of the what do you call it, sketch notes that have been turned in and stuff. They're up to date, and those are all graded. You know, if you need to still turn in a sketch note here or there, that's totally fine. And I'll be reaching out. There's a few people. I don't think anybody that's here, so it doesn't matter. But I need to reach out to a few folks to make sure I get a little bit of stuff and make sure that everyone is doing okay, and see what I can do to help make sure everybody can be successful here. So what we're going to be talking about today is earthquake magnitude and intensity. And so we're going to be looking at the difference between those two. We're going to be talking about hazards and risk, kind of comparing a couple of different earthquakes and trying to basically understand how to stay safe. And this is the whole point of talking about this, and why we spend, you know, kind of the 2 weeks on the earthquakes here. Is I just think it's a valuable thing, especially if we're living in California, growing up in California. We need to know how to stay safe, and we need to know how to tell others how to stay safe. We need to, especially if any of you end up going into politics or anything, or in a position to help steer a school board or something like that, and how to make smart earthquake decisions, you know, whether it be buildings or what to do. I think it's a super important and invaluable thing to learn about here. So like I said, mad props for everybody being here on a Friday. Thank you. I know it takes a lot, especially halfway there. Batteries are running low. So hopefully we can have at least a little bit of a good time tonight. All right, looking at these earthquakes, or at least I don't know about a good time, but imagining good times that will be prepared with earthquakes, and seeing some very interesting video footage and images. All right, so we'll talk about how to measure quakes, the difference between magnitude and intensity. We'll look at some earthquake hazards, and then be able to look at some earthquake risk assessments. I'll show you some interactive maps that California has put out now that will do some really good in terms of, you know, if you decide to live anywhere else outside of Turlock, or even in Turlock, what are some of the risk assessments that you might need to ask yourself before you move into any of these other places. I would show you the sunshines and blues from last week, but I think I forgot to give them to you, so that's why there's none. So other than that, kind of happened. It seems like a long time ago now, but on Monday we had that huge wind event. I think I was telling you about it on last Friday. I mentioned it, but in Turlock, we had a peak wind gust. This was before the peak one, but we had a peak wind gust of about 41 miles an hour down just on the southeast end of town, or southwest side of town. No, southeast, yeah, southeast side of town, which was pretty strong. On the west side of the valley, it was like in the 50s. One of our neighbor's trees, huge, big pine tree branches fell down and broke and smashed a little bit of a car. So hopefully nothing too bad happened to you guys. And you know, speaking of weather, since we're on that track, it's been 209 days since we've had measurable rain in Turlock, and in Sacramento is kind of the same case too. So here's the upgrade and the update, and kind of good news-ish here is that signs are looking good 6 to 10 days out for possible wetting rains. So like maybe next Friday by this time, we might be talking about storm systems starting to push in. And these numbers here represent maybe possible maximums of like what the storms will produce in that given time. So like almost an inch of rain, which these models tend to overstate things. But I mean, if we ended up with a half an inch of rain, that would be great. But in the northern part of California, if we got this much rain, even an inch or two, it would do a lot to help basically end the fire damage or the fire danger for this year up in that part of the Sierras, you know. So that would be great if that could happen. And I would just want to go outside and it's raining, feel the raindrops and go crazy and smell that smell, the petrichor. And that's the name of that smell when it first rains. Just is such a great smell to me. So something to look forward to. And then last but not least, I just want to, even though I haven't mentioned it in a couple of weeks, La Palma, the Cumbre Vieja volcano in La Palma is still going very, very strong. And I just want to show you here, this was from a few hours ago. Oh, I guess about 10 hours ago now, but the daytime over there. These are the flows still coming out. Each one of these now is about 15 to 20 feet tall. These are really massive flows that are just creeping down the houses. And what's pretty amazing here is they've also had a few new vents open up, and lava is just kind of, it's like a little lava tsunami washing out here. It's not a real tsunami, but just really low viscosity lava started flowing out, which is pretty amazing. And it's hit the ocean. It's made this big lava delta out there, and it's still building new land as we speak. And as of about 3 hours ago, it started opening up. This is a thermal image. So here's the lava flows coming down through here, and it looks like a new vent opened on one of the flanks of that cinder cone. And they don't know yet if it's a lava flow or if it's like pyroclastic flow coming down. But they're doing a whole bunch of looking for ash and monitoring the ash every day. So this is their scientific method, right? It works. You just basically put a Tupperware out on top of a pallet that's held down by rocks, and the straps also keep the bucket from blowing away. And each day, every 24 hours, they go out and they just pour out all of the volcanic ash and the cinders and stuff that fall down in that bucket, and then they pour it in the bag, and that way they can measure the volume, how much there is, and what stuff is coming out. So I thought that was kind of cool, and want to let you know that it's going totally fine. And I don't know why these shirt ads are up there, but that link, this is a link to the Weather West that talks about the weather coming up in the next few days. That was on the previous slide, if you want to take a look at it, which is right there. If you click on that link, it'll tell you all about what to expect if you're really interested. All right. So then for today, for the sketch notes for this week, basically, what we're kind of looking at is how can we measure earthquakes and how can society understand and mitigate those seismic risks. So some of the things we'll be looking at is the difference between magnitude and intensity. And you'll see here, it's like, what does it measure? What are the units of measurement? Things like that. Try to find a way to, put a few sketches in here too to bring this to life, so it's not just necessarily writing everything. We're going to be talking a little bit about seismic waves and the amplitudes, which basically are asking you, what type of ground or soil will seismic waves have the greatest amplitude in? What types of ground and soil will the seismic waves have the smallest amplitude? So we'll see later on, but I'll just tell you right now, amplitude is basically how high are the peaks on the ups and downs of a wave as it goes through. So a higher amplitude wave is like taller, a smaller amplitude wave is smaller, like that. Then we'll be looking at these 6 different earthquake hazards. So give some sketches, descriptions, how we can reduce those risks when we talk about that. And then kind of the interactive part of this, or the extension part, is if you can imagine you had the good fortune of being able to purchase a house from which to remotely work, but you had to choose from one of these 4 places, which is Turtle Rock, Santa Clara, Eureka, which is near the beach near Eureka, California, or the Sierras near Lake Tahoe. What questions would you ask your realtor or apartment manager or whatever regarding earthquake hazards in each of those cities before you made your final choice? All right, so you can choose whichever one of these places you want to live in, but if you were able to choose there, you had all the mad money in the world to spend on it, but you wanted to be earthquake safe and you wanted to make sure your investment was going to be good and that everybody in your family is going to be safe if there was an earthquake, what type of questions would you ask them? So it says support your questions with reasoning for why you'd ask them those questions. And you can either feel free to write it or sketch it in a comic form, or you can just kind of give me a little narrative. But the thing that you're going to be looking at is this interactive map. And I'll be showing this to you again in detail here in a few minutes later on today. But these are basically earthquake hazard maps you just click I agree. This is from the California Department of Geological Survey. And you can go in and see all sorts of different hazards in these different areas by clicking on them, and it'll tell you what's there, which is pretty cool. So we'll see what these colors mean later on this afternoon, but this is the interactive map that you can use to help figure out to answer some of those questions. Okay. So, and if you see me catching my breath here too, I think it's leftovers from some of the vaccine shots and stuff. Like it's just shortness of breath type thing here. But so I'm trying to breathe a little bit, but it's knocked me on my keister a little bit. But anyways, what we're going to talk about first tonight is measuring the magnitude of earthquakes. So last week we talked about the P waves and the S waves and how those are the body waves moving through the earth. And then we talked about the surface waves rolling through on the top. But what we didn't really talk about yet was how big these earthquakes are, or what constitutes how big an earthquake is. So we have two different ways of measuring it, right? And so the first one is the magnitude. And the magnitude used to measure the size of seismic waves, which basically measured the amount of energy released by an earthquake. All right, so that's all they used to measure in the past, was the height of these amplitudes of these big, like the S waves and some of the body waves that would come through there. But now what we were able to do in the late 1970s, or seismologists were able to do in the late 1970s, is they were able to start tying together how big these earthquake waves were with how much ground actually broke and moved, like how much area was displaced in the earthquake. And it turns out that was a much better way of measuring the earthquakes, because the old, you may know of the Richter scale, the old Richter scale there, it kind of lost its ability to measure big earthquakes. If it was a really big, like if it was like a magnitude 8 or magnitude 9, it was hard to tell the difference between that and a magnitude like 7 or 6. It was just kind of blow out the bass notes, I guess would be a good way of putting it in like musical terms. You just blow it out and wouldn't be off the charts, and then you wouldn't know what it was. So they were able to figure out how to do a better job of measuring it based on the amplitude with new seismological equipment. And so just to kind of give you an idea of what some of these earthquakes are like when we're talking about them, this was a 7.8, I think, 7.8, 7.9 over in Kathmandu Valley in Nepal. And this was, I think, 2015, yeah, April 2015 here. So check this out. I just want to show you what it's like if you were to experience a big earthquake like that here, maybe. There we go. And I'm gonna turn down the volume here on this one just so you guys can see it. But there's a couple of things. Oh, 7.8, that's what it was. I don't know why I always forget that. But it's showing the GPS station. You'll see the GPS station pop up here in just a second. And that's going to show how far up it moves, how far down it moves, to the east, to the west, north, south, things like that. All right, so you'll see that here in a minute. But here's the scene. I just want to set the scene. No shaking yet, but look at you can see some of the buildings here. Looks like concrete. And I just want you to kind of take a look at this part of the building too, as the video keeps playing here. So here comes the GPS station. You can see here's the north, here's the east. And there's the P waves. You can see the waves start hitting, and then these people know what's up. And then boom, here come the surface waves, right? And when we say it's hard to walk and hard to run in like big earthquake, this is why. The ground is literally heaving up and down and all around. And you can see this is a meter of displacement. So in some places it was moving, over 6 feet as it was moving up and down and to the left and to the right, which is just pretty amazing to think about. So they're minding their own business. And I don't know if you all saw this part here, but this lady, right? Well, not her. You'll see another lady come right around the corner, right? Oh, there, woo! And then boom, there comes the concrete. So this is a pretty big earthquake. 7.8 is a pretty large earthquake here. And it caused a lot of buildings to collapse in the area for sure. This is happening at a convergent plate boundary where the Himalayas are being created and pushed up here. But how do we know how big this was, right? Well, that's where we started looking at the seismographs and figuring out how big the squiggles were. So there is one thing I want to show you that's better than me explaining it, I think, because this has pictures, but it'll show you how we measure the magnitude of the earthquake and how we kind of took Richter's old scale here and modified it to become what we see today. So it's called the modified or moment magnitude. All right, so check this, what the heck, check this out. And let me put on the sound and share my sound.
Like not being able to hear the bass notes on your laptop speaker. That meant that the Richter scale underestimated the size of large earthquakes. Seismologists have since developed far more sensitive seismometers that, with faster computers, have enabled them to record and interpret a broader spectrum of seismic signals. These improvements allow them to better determine the energy released by large earthquakes. In 1979, they connected the seismograph recordings with the actual physical displacements that occurred during an earthquake. The result.
So basically, in order for that to happen, I just want to say they had the earthquake, they had the recordings, then they went to where they knew the fault was and dug a trench for the fault and actually measured that whole entire fault to figure out how much had been displaced. And then they started doing that to other faults. And with that, they were able to match what happened in the ground to what the waves were happening on the seismographs. All right.
Was the moment magnitude scale. Seismologists no longer look at only the amplitude of seismic waves, but instead use much more information contained in the seismogram to calculate what is called the seismic moment. The seismic moment, which defines how much force is needed to generate the recorded waves, is defined by this equation: mu times distance times area. Mu is rock rigidity.
So here's the thing. I don't want you to memorize this formula. You don't have to know these calculations. But what I do want you to know is kind of this basic equation here, and is the fact that the rock rigidity, or how strong it is, or how resistant it is to being compressed or sheared, that multiplied times how far the earthquake has moved and how much area of the earthquake was ruptured, or how much fault ruptured. That's how we come up with this magnitude, like a magnitude 6 or magnitude 7 or something like that.
Describes the resistance of the rock to bending when force is applied and is a constant for a given rock material. More elastic energy is stored bending rocks of high rigidity than is stored bending rocks of low rigidity. For example, this brick has high rigidity and when bent or sheared would yield a strong earthquake. The cake has lower mu and shears easily. Rock rigidity is lower in the crust than it is in the mantle. As mentioned earlier, in most cases, distance and area can be determined by mathematical modeling of seismograms. D is the distance that the rock slipped along one side of the fault zone relative to the other side. In the 1906 San Francisco earthquake, this fence line was offset over 3 meters.
So it was offset over 3 meters, but remember that fault that ruptured, that happened over 100 miles in length, just about, I think, if I remember my numbers right. So somewhere right in that neighborhood of about 100 miles long of fault moved 3.5 meters, right? So along that 100 miles, everything was offset, in this case to the right. So it's a right lateral fault here, about 3, did I say feet? I meant meters. So that's about 11, 12 feet, somewhere in that neighborhood.
A is the estimated area of the fault zone along which the rock slipped, the distance d. It defines the area that actually ruptured during the earthquake. Let's watch an earthquake happen. The arrows show forces building on opposing sides of a fault. Growing stress that will be relieved in the earthquake will be shown in red. Here we see blocks of rock move in opposite directions along a strike-slip fault zone, such as the San Andreas Fault in California. Potential energy, in the form of elastic energy, is stored in Earth's crust or mantle, building stress as the ground slowly deforms between large earthquakes. Take a look below the ground at the earthquake rupture that defines the seismic moment. That equation is then plugged into the moment magnitude equation, which is used by seismologists to measure the size of earthquakes in terms of the energy released, not just the amplitude of the recorded waves. The constants in the moment magnitude.
So that's the big thing, is the energy release. That's what this is measuring. So if you know how much of the fault has moved, and you know how far it's moved, and you know how strong the rocks are, you can calculate how much energy was released. And that's how we calculate how big or how small the earthquakes were. So I want to show you I'm just going to skip a little bit to here to the good part, which is right here. So check this out.
Scaling, we'll look at the effects of the rupture area by using PASTA as a model for magnitude.
So they're going to use these pastas as a model of magnitude, just like they said, but we're going to pretend that this pasta represents like a magnitude 5 earthquake by the amount of energy it takes to break one pasta noodle and move it a millimeter. We're going to pretend in our model that's going to make a magnitude 5 earthquake. So how would that compare to like a magnitude 6 or magnitude 7 or magnitude 8? And that's what this video is going to show you, how to compare those, okay?
The cross-sectional area of a strand of spaghetti is about 1 square millimeter. When you break the noodle, it makes an earthquake of, let's just say, magnitude 5 for our model. Mu is constant for all strands of pasta, and for D, we'll use 1 millimeter of displacement across the fault. So here we see the pasta break and move laterally 1 millimeter. To increase it to a moment magnitude of 6, we multiply it times 32. The surface area is 32 times higher, yet the amplitude is just 10 times higher.
So the reason they're multiplying it by 32, it turns out in this scale to go from a 5 to a 6 or go from a 4 to a 5, when you increase 1 unit of magnitude on the earthquake scale there, or on the moment magnitude scales, it's an increase of 32 times the amount of energy. So it takes 32 times the amount of energy to go from a 5 to a 6. It takes, if you go from a 5 to a 7, you have to go 32 times to get to the 6, and then 32 times that to get to the 7, which you'll see is nearly 1,000. So check this out.
To reach a magnitude 7, you have to multiply 32 times 32, and you get roughly 1,000 strands, or about a pound of spaghetti noodles. To get a magnitude 8, you need 32,000 pieces of spaghetti.
And a lot
a
of
magnitude 9, on the other hand, would require 1,000,000 pieces of spaghetti. A magnitude 9 releases 1,000 times more energy than a magnitude 7 earthquake.
So this is something to think about here when we're talking about these scales. The magnitude 9, like they said, it's 1,000,000 times greater than a magnitude 5. It's 32 times greater than a magnitude 8. So you would need 32 magnitude 8s to equal the energy of one magnitude 9. And so when we had the magnitude 9.1 or 2 quake in Japan a few years ago, like in 2011, a few years ago, it's been 10 years now. But when they had, it was a 9.1 or so, that earthquake alone released more energy in that one earthquake than all the other earthquakes on Earth combined for like a year and a half prior or something like that. That's just how massive it was. And that's what we're going to try to get our heads wrapped around here, is it's so hard to think about how big these scales are going forward. So I have a way to help us better understand these here in just a second. And so this is kind of the words that, if you didn't catch it in the videos here, but the magnitude measures the amplitude of the largest seismic waves as well as the offset area of the fault here. That measures the area of the fault and how much of it was offset. And from that, they can now use those amplitudes and the waves to understand how much was offset and calculate within seconds of how big the earthquake is. So with that magnitude scale, it's a 32 times increase in energy for each magnitude that you go up from, like a 1 to a 2 to a 2 to a 3, et cetera, okay? Kind of the old Richter scale, and what we still sometimes look at, the seismic wave energy, or the amount of shaking on the seismograph there. Each magnitude that you go up, the size of the amplitude of the shaking goes up 10 times as well. All right. So if you went from a 2 to a 3, a 3 would be 10 times the amount of seismic wave amplitude, but 32 times the amount of energy. If I went from a 2 to a 4, I'd have to go 10 times 10, which is 100. So 4 is 100 times bigger squiggles on a seismogram than what you would see in a 2, and it would be 1,000 times more energy released in that thing. So that's a lot to keep in track of, right? Like to calculate that and do all that other stuff. But luckily for us, the USGS has a really pretty slick little calculator here. And so that's going to be our first breakout tonight, is you guys are going to choose 3 different earthquakes, and I'll show you where to choose them here in just a minute. And basically what you're going to do is you're going to calculate how much bigger is a magnitude. Let's say it starts with an 8.7 and a 5.8, but you can just type in any size earthquake if you want. So let's say like a 7.9 or something. How much bigger is a 7.9 than a 5.8? Well, you just click calculate and it does all the math for us, which is so lovely. And it says the difference between the magnitude is 2.1, right? So that means it's 125 times bigger. So the seismic waves would be 125 times bigger than the magnitude 5.8. But it's 1,412 times stronger. So that means you'd need 1,412 magnitude 5.8s to equal the same amount of energy released in one magnitude 7.9. That's how you read this. All right, so here's what's going to happen. Let me put this in the chat here. Calculator. Oops, let me, there, oh, I thought here we go. And I didn't come up with the name or anything like that. That's just, I would call it like an earthquake calculator or something like that. I just don't think it's super intuitive. But anyways, there's that. So you can click on that in just a minute. And then the other thing you're going to be doing is we're going to be getting into our breakout rooms with this. So here's a Jamboard. And it should, I mean, this is not going to be a super long one right here. But you're going to get into groups with this Jamboard. And on this Jamboard, you are going to choose 3 different earthquake locations amongst your group. And you're going to say, okay, here's the quake number 1, the magnitude, location, the depth, right? Magnitude, location, depth, magnitude, location, depth. So choose 3 earthquakes anywhere. You know, like, well, Hollister, where am I going to choose those 3 earthquakes from? Well, I'm so glad you asked. Basically, where you're going to choose them from are the earthquake viewer. So, oops, not the one we've been using the last few days with the other earthquake stuff, but this earthquake viewer actually is the USGS one, and it's pretty cool. And it has all the earthquakes anywhere in the world that have happened in the last week or so here. Or do I have, I think I might have it turned on the last 30 days. What I hope, sorry. If you click on the little sprocket thing. Yeah, so this is 30 days, all magnitudes US, so big and small, all around the world. If you see a red one on there, that means it's happened within the last hour. And you can take a look at all these different things. But if you zoom out, you can choose any earthquake that you want. All right, any earthquake that you want on there. And you choose those 3 different earthquakes. Oh, well, what was this one? I missed this one, did I? Yeah, okay, anyways, so you choose all these 3 different earthquakes, and you're going to go to your Jamboard here, and oops, where'd it go? On that, wrong one, sorry. On that Jamboard, you're going to say, oh, quake 1, it's a magnitude, so you can go back to here. If I chose this one down in Indonesia, I'd click on this, and it pops up over in the left-hand corner over here, and say, oh, it's a magnitude 6.4 near Buala, Solomon Islands. And then that's all you need to type for that. And then you can say its depth was 22.6 kilometers down. So that's all you need to write down on the Jamboard for that piece, right? Is the magnitude, its location, and its depth. Once you have all 3 of those on there, then you just pull up the calculator and you enter in the differences between, like, you compare number 1 to number 2, and then number 2 to number 3, etc. And you're going to calculate those differences to figure out how much bigger or how much smaller things are. And then you just put that information right here, and we'll move on from there. So it talks, basically, you're just filling in the blanks that are in here. So the difference between quake 1 and quake 2 is blank. It is blank times stronger, but is, or magnitude, it is blank times bigger, but it is blank times stronger as well. And that's what you just kind of fill in. So we're just doing this to compare. It should take, like, I don't know, 10 minutes or so for this one to go through. It's not supposed to take a whole heck of a lot of time. So explore some of the earthquakes, find the ones that you want. If you want, each person can choose one, and then put it on the Jamboard, and then do the calculators and calculations and see what we come up with, right? Because we got to know this a little bit before we move forward, so we have this in our brains before we start comparing the intensity of things. So let me put you into some breakout rooms here. And let's see here. There we go. We'll do 4 groups. So there'll be one group of 4, and we'll just move from there. And you might have some questions about things that pop up down on those areas, and we'll answer those as well if you need to. All right, so we'll do 4 breakout rooms. Let's say somebody just came in. So I think we can do, let me see here. Yeah, 1, 2, 3, 4. Oh, there we go. Yeah, we'll do that, and we'll be good to go. All right, so about, let's say 10 minutes here, and see what we can do in 10 minutes. If we need a little bit more time, we can do that too. And let me put that in room 2. All right, and have a good time. Say hi to everybody. Sarah, are you here or? Okay. Oh, hi, Sarah.
I'm still in the breakout rooms, but
Oh, okay.
I'm on my phone. There was like some random 2 dogs that came to my house, and like we had to like go find their owners or something. And he finally pulled up with the truck right now. That's why it took so long going into the breakout rooms.
Oh, yeah, no worries. No worries. Do you need help getting back in or anything? No, or?
I'm still in my breakout room on my phone, but once I leave here, I don't think I can go into that same one. But I'm in room 2.
Okay. I'll just put you. I'll put you in room 2 in this one too, and then you can figure out what you need to do from there.
I just left my phone one, so I think it'll be good.
So do you want me to put? Oh yeah. So it's like you've disappeared out of the other one now. So.
So now I just need to be put back into it.
Yep. Okay. Here you go.
Thank you.
Hi, Clarissa, are you there? Or
Hi, sorry, I had to disconnect because I lost signal. I'm driving and I'm on the Altamont, but
oh,
I'm back now.
super fun. No worries. All right.
Is
Yeah,
everyone in a breakout room?
yeah, well, yeah. And so we'll be coming out in just like 20 seconds or so here. So I'll just keep you here and then we'll come back.
Hi.
All right.
Okay, sounds good.
All right. Welcome back, everybody. So good job. Let me share my screen again. Good job. I think it takes a little bit of getting used to some of these things the first time around for sure. But y'all did a great job there. And let me make sure. Okay, there we go. Hanging in and making sure that we got some of these. So I thought it was kind of interesting. I think a lot of folks see the earthquake map and they start finding really cool stuff. Like somebody found an explosion, which are like from quarries and mines blowing up stuff, and we can record those as small earthquakes if they're big enough booms, for sure. But I think it's a good exercise to just go through this and see. And when we're talking about magnitudes, we're purely talking about the size of how much fault has moved, basically. All right, that's the big thing we're talking about, is how much area of the fault ruptured, how much did it move, and how much of the seismic signal did it create. But what we're going to see now, having done that, what we're going to see now, if I can choose the right tab here, is magnitude's only kind of half the story here. And so what's kind of interesting is we have another way of measuring earthquakes as well, which is called the intensity. And so the intensity doesn't necessarily rely on instrumental recordings, right, of how big the shaking was or how much fault moved or things like that. What it does measure is the amount of observed. So when I say observed, like what you felt, observed shaking and the observed damage that an earthquake created. And so really the intensity scale is based on how much destruction did an earthquake do. And the reason we do this is because we can have relatively small earthquakes, magnitude 5s, that can actually be very deadly if they hit in areas where the soil's not correct or the buildings aren't necessarily built to withstand earthquakes and things like that. So you can have really small earthquakes be really damaging and deadly. You can also have really massive earthquakes like that magnitude 9.1 in Japan in 2011, where it's a huge magnitude, but the amount of deaths were very fairly low, and most of them came from tsunamis that washed ashore a little bit later on after the earthquake happened. But that's because the buildings were engineered to withstand a lot of those different shakings that happen. So that's why we came up with intensity, is because the magnitude alone, or the amount of energy released, doesn't always determine how bad the damage is going to be up high. All right. And so this is this picture is from China back in 2008. And it was a relatively small magnitude earthquake. And I'm trying to remember, I think it was in high fives or low sixes, but it caused catastrophic damage to a lot of concrete buildings and unreinforced older buildings that weren't up to modern earthquake codes, which have since been upgraded after this, so it doesn't take much. And kind of the way I remember intensity, it's always been my mnemonic device, and kind of not to be glib or make fun of this or anything, but intensity kind of ends up leading to a lot of tent cities, and while the earthquakes and the aftershock sequences and things are happening afterwards. Because once you have a really big earthquake, like this one was in Chile in 2010, so is a magnitude 8.1, I think 8.2. And they have very good engineering construction standards, earthquake standards in Chile. And yet some of these big buildings still toppled and fell. And then you have large aftershocks that happen afterwards, magnitude 6 aftershocks, or greater. And so you can't be any of those houses or any of those buildings that are structurally unsafe, because you risk collapsing during an aftershock. So you go to fields, you go, they have the camps that they set up, and they feed folks out here until it's safe to go back to their houses. So when it's a really hugely high intense area, it usually leads to folks living in little tent cities for times being. And it just depends on the countries. We talk about equity and just ability to access resources. Chile was pretty good about this and was able to create things like this. But after the Haiti earthquake, we'll see in just a few minutes here, it took a worldwide effort to try to get things even up and running in Haiti again after that magnitude 7 earthquake, which caused a huge amount of destruction, which I'll show you here in just a second and talk about it more. But so I digress. So the modified Mercalli intensity scale, that's how we measure intensity. So you'll notice it goes in Roman numerals here. So it's different than the magnitude, which are straight up numbers and decimals and stuff like that, right? The intensity is measured on a 1 through 10, and sometimes can be even greater than a 10. So all the way from not felt to very extreme. So we always know when we're looking at the magnitudes here, like this one says magnitude 7, but we can see the colors and the shades here show what the intensities were like as the earthquake moved out. So here's a better way of describing all of those in terms. This is from the USGS, but this is what we call the modified Mercalli intensity scale. Mercalli was an Italian person who came up with this back in the mid 1800s, the original kind of damage scale for this. And then it's since been modified to become adopted around the world. It's pretty uniform around the world. So you can see, like, extreme basically means some well-built wooden structures are destroyed. Most masonry brick buildings are completely destroyed, things like that. Where you compare that to like a 7 on the Mercalli intensity scale, if you have buildings that are good designs, not much damage. But there could be considerable damage to poorly built or badly built design structures. And so let me show you kind of what this would look like in real life, right? So this would be kind of an intensity of a 4 or a 5 using those Roman numerals. This was after an earthquake in Nevada 10 years ago, I think, somewhere in that neighborhood. But this is the one that it shook enough. It's a magnitude 6 somewhere in that neighborhood, but the intensities was only a 4 or a 5 because it was far enough away from the epicenter where it just threw all of the like looks like shampoo or something like that on the floors there. So that's, you know, intense enough to cause things to fall off the shelves, but the buildings are fine and it's just a nuisance, right? Well, if you compare that to an intensity of like an 8 or a 9, this is in Wells, Nevada. And believe it or not, all you can see the brick buildings again. This is a kind of a historic old Western type town in the middle of Nevada. Not many folks still live there, but they had that earthquake back in 2008 or 9 or 10, somewhere in that neighborhood. And all the building faces just collapsed. And what's so kind of weird about this picture is when I took these, it was a year after the earthquake had hit. So it had been basically standing like this for a year after the earthquake. They just didn't have the financial means in the community or the county to clean it up. They didn't have the ability to tow it away. They had to fundraise for a long time before they could finally get the money to bulldoze everything and make it better. So that's like an 8 or a 9. So you can see kind of the older buildings that are made of brick collapsed. And then on the extreme side of the scale here would be Haiti, which is super duper intense here. And the Haiti quake, like I was saying, the initial quake itself produced a lot of not low, but high frequency seismic waves that were running through the area. And it just so happened that the waves of the frequency or the period of those waves going through matched the ability of the buildings to wiggle and shake. So if you have kind of shorter buildings and you have smaller wavelengths, they vibrate in what we call resonance. And I'll show you a quick little video on that a little bit later on this evening. But because of that, because the earthquake waves kind of matched the height of the buildings and the resonant frequency, it caused a lot of them to just wiggle, wiggle, wiggle. And because they were made out of concrete and unreinforced, there wasn't much rebar and things like that in there. The concrete pillars just collapsed, and that allowed all the other buildings to collapse on top of it. And this is one of the deadlier earthquakes that happened in the last 100 years or so. It killed over 200,000 people, and it wasn't just the smashed buildings. I mean, that was a big part of it. But what really caused so much trauma afterwards was, the ports were closed for a long time because they were completely damaged. The airport was damaged. And so trying to get goods and services in there to rescue folks in an already fairly impoverished country that didn't have a lot of like excavator equipment and things like that, it was hard to get there. And so once it finally got there and World Aid and the United Nations started coming together, one of the big missteps was the United Nations folks started setting up their troop camps and their aid worker camps right next to a creek. And they also set up a lot of their latrines and things near there because, right, there's no working sewer system. So you have to put pit toilets. And some of those latrines started leaking into the creek. And there was no other water sources, or not very many other water sources on the island. People, after this has crashed, are looking for things to drink. So they drink out of the creek, and it started spreading cholera. And so there was a huge cholera outbreak that killed so many people on the island as well after the earthquake happened. So this was just a really tragic, tragic, tragic earthquake. And they had another one happen just, 2 months ago that was of similar magnitude and not nearly as devastating because it didn't hit well, you guys are going to try to figure out why it wasn't quite as devastating, but Haiti just can't catch a break is the kind of the main message here. And as earthquake scientists and geologists, you just want to do your best so people can be prepared so that we don't have to have that kind of suffering. That's why a lot of folks go into the business of earthquake sciences, to save people, right? So here's what we're going to be doing. We are going to take a quick 5-minute break. So it's 5:30. We're going to take a quick 5-minute break, go stretch your legs, go do whatever you need to do. And then when we come back, we're going to do our second little breakout group. And within that, you guys are going to be comparing the Loma Prieta earthquake of 1989 and the Haiti quake of 2010, which are very similar. And we're going to try to come up with some ideas of why the intensities might have been a little bit different and death tolls and things like that. All right. So with that being said, it's what time? It's 5:31. So let's come back at about 5:36. Go take a break, get a snack, whatever you need to do. We'll come back at 5:36 and we'll pick it up from here. Okay. You guys can still be on break. I'm just getting a few links ready for this here. Alrighty, so it's 5:36 here. So here's the next little bit, and I'll just talk a little bit as you guys start filing back here. All right, so here's the next little bit that we're going to be doing. Oops, what the heck? Where are we at there? Here we are. So like I said, you guys are going to go into your breakout rooms. This is going to be a pretty short breakout. Again, not super long or anything. But we have the Mercalli maps from the Loma Prieta earthquake and the Haiti earthquake. This is the one in 1989 that destroyed the World Series. Kind of like the Dodgers destroyed last night, which is terrible. And then it didn't destroy the World Series, but it destroyed some of the highways during the World Series. And then the Haiti 2010 quake, which is right here. So the stars on those maps show where the epicenter was, so where the actual fault rupture broke, all right? And then the colors show the severity of the shaking based on the Mercalli scale going out. So here's a couple of comparative things to think about. Is the Loma Prieta quake 6.9? Haiti was a magnitude 7, so almost identical magnitudes here. In this quake, 57 people died in Loma Prieta, 22,570 died in Haiti. There were 12,000 homes destroyed in Loma Prieta, 93,000 destroyed in Haiti. And they had, a max intensity of like 9 here and a max intensity of about 11 in Haiti. So my question for you, if you go to that Jamboard, I think I put the link in, but let me double check. And there it is. I'll put it in again. If you go to this Jamboard in your groups here in just a moment, what I want you to do is we kind of compared the earthquakes already. I just want you to create 3 hypotheses really quick as to why you think the intensity and the damage was so much greater in Haiti. So if you want, you can take a spin on the earthquake pages. There's the links right down here. So if you just copy these links, so let me show you what this will do if you do that. If you get those links and you paste them and put them into here, what? Undefined. Well, oh, there it is. Okay, it just took a second here. So you can click on this and it'll give you an interactive map to show also where the shaking was most intense. But if you click on this map, you can go to topographic or street or something like that, or you can even go aerial images, and you can see just how, here's Port-au-Prince, which has a couple million people in it, I think, or over 1 million people. There's their airport. So you can just see how densely populated it is. And you can expand and check those out if you want to take a look at those maps as well. But just come up with 3 quick ideas, 3 different ideas of why you think one was more damaging than the other. All right. So think about anything that you can think of, and that's what we're shooting for. So we'll do about 7 minutes or so. I think should probably be plenty of time for this, and we'll see how you guys are going and come back from there. So I'm going to reorganize a little bit. Some folks have gone away, so I'll open these up, and I think I'll combine room 1 and room 2, and then we'll be good to go here. All right, so 7 minutes, oops, not 47 minutes, 7 minutes, and we'll see how this goes. All righty, and then, and there's a few people that haven't been assigned to a room yet. So let's see here. Let's see. We'll do 1, and we'll do 1 like that, and then I think we'll be okay. Marisol, are you here? Are you okay? Or okay, there. All right, there we go. So great job. I know it takes a lot of time, and we haven't, sometimes to think about stuff and come up with some ideas. And I liked, so I'll just kind of go through and see some of the main topics and things that we came out with. But group one was talking about how Haiti is a very maybe poor country, and maybe the buildings weren't properly built, so more likely to collapse. And maybe it had something to do with Haiti sits on a fault line between two tectonic plates, which causes stronger earthquakes and more destruction, right? That definitely could be part of it. But one thing I will say is, like, turns out that it sits on a strike slip fault, very much like the San Andreas sits on a strike slip fault right here, which both separate the tectonic plates. So interesting, right? Like, so kind of cool to think about. And they're both about magnitude 7s. So these are good ideas and good thoughts to start off with. And then another group mentioned that this one was stronger, and that maybe that Haiti is smaller compared to Loma Prieta in California and surrounded by water. So my thinking here is probably that with that there's more water here. Maybe it had something to do with increasing the damage, and we'll see later on how water can increase the damage, like from tsunamis and stuff. Maybe there's more landslides or liquefaction occurred more there, so that's a really interesting take, which was kind of cool. Maybe the buildings weren't as stable for group 3, right? So maybe they weren't as able to withstand some of those big ones. And then somebody also mentioned here in group 4 that in Haiti, there aren't very many seismic networks, and they didn't have as many seismologists, which is completely true, and therefore made it hard to prepare for an earthquake. And so I went to the other seismic explorer we were looking at, and starting in 1980, if we kind of spread our timer going down the timeline here, you can see, right, even up through 2000 and stuff, Port-au-Prince and Haiti down here, there wasn't too many giant, massive earthquakes, but there's a subduction zone over here, and there's a subduction zone a little bit over here, and those convergent boundaries, and stuck in between is Haiti on these strike slips. But you'll notice, look at that. I mean, just all these earthquakes happening over here, not so much over here, not quite as much. And then 2010 happens, boom, you can see the big earthquake happened like this. There it goes. And then all of these are aftershocks that started coming. And in the years following, we have all those aftershocks, and not too much. And then just this last month, or 2 months ago, when was this? In August, we had magnitude 7.2. But here's the thing about this one, this magnitude 7.2 was still damaging, but it was not nearly as damaging as the one that happened here. And part of it has to do with the proximity to the population in the area that was there as well. So these are great ideas, and it turns out the things that really control the intensity are how close the epicenter is to a population center, how deep the earthquake magnitude is, right? So the shallower it is, generally the more damaging it's going to be, because it doesn't have to travel through as much rock to get to the surface and shake. That's kind of one big thing here. The type of soil that stuff is built on, or the type of rock, definitely plays a role. And yeah, the building codes are also a massive controller of all that damage that can happen. So that's what we're going to be thinking about as we move forward here, thinking about the difference between earthquake magnitude and intensity. So here's a really cool little video clip that should help you maybe kind of remember what the difference is moving forward.
Magnitude and intensity are both related to the size of an earthquake, but they each measure different aspects. Magnitude, which measures the energy released at the source of the earthquake rupture and is calculated using measurements from seismic instruments, is one single value. Seismic intensity, which is the measurement of the strength of shaking at a specific location, determined from effects on people, human structures, and the natural environment, produces a range of shaking intensities in different locations. Thus, Unlike earthquake magnitude, which is the same for all locations, the seismic intensity you feel depends on where you are. Intensity is mostly controlled by three factors: magnitude, how big the earthquake was; distance from the hypocenter, intensity varies from place to place; and the local rock and soil conditions. Let's compare magnitude and intensity by using a light bulb as an analogy. The light bulb represents the location within the Earth called the hypocenter, where the earthquake begins. The magnitude or size of an earthquake is like the wattage of a light bulb. Just as the wattage represents the amount of power of the light bulb, the magnitude is related to the total amount of energy released by the earthquake's source. The intensity, or shaking level, is like the amount of light from a light bulb at any spot in a room. A small light bulb in one area of a room will make that area bright with high-intensity light, but it will leave the distant areas of the room dim with low-intensity light. So, a given earthquake has only one magnitude, but will produce different intensities of ground shaking, as shown on the USGS Did You Feel It intensity maps.
And so that's kind of cool. After we have an earthquake, you can go onto the USGS, the US Geological Survey, and the Did You Feel It? And you can start filling out these forms that then help them better calculate what the shaking effects were like in a given area. So here's the 9.2 quake in Japan from, when was it? 2011, right? Yeah, 2011. Oh yeah, here it is. The Great Honshu quake, magnitude 9.1. But you can see this, the epicenter was out in the ocean, but there was still in some places some relatively strong shaking. And then the further away you get from it, the much less shaking, right? That's because it just kind of loses energy as it propagates out and away. So the bigger the quake you have, the more likelihood you're going to have a higher intensity. The further away you are from it, the less likely it's going to be intense. But if you're close and right on top of it, it's going to be a pretty intense thing. The depth of the earthquake matters, and I'll show you a quick little video on that in just a second. If you have loose rock, that definitely, soils and mud, that is definitely a lot weaker and shakes more during an earthquake compared to solid rock. And then our building designs and how many people live in a given area. So in that Haiti earthquake, it was right next to a huge population center. And in Loma Prieta, it was in the middle of the Santa Cruz Mountains, and it was a good 40 miles away before it reached any of like super populated areas here in San Francisco. And so there's the Did You Feel It page that if you ever feel an earthquake, you can click on that, and it'll assign you based on your survey what the shaking was like in your house, which is pretty cool. All right. So with that being said, that's the difference between intensity and magnitude. So we're going to end the night here talking about a few of the major hazards in the earthquakes. And so some of those major hazards that we're going to be looking at are the ground shaking and structural damage, surface ruptures, liquefaction, landslides, fire, and tsunamis, which are pretty amazing and pretty, I just find them so interesting. Everything of this is interesting, I think, but tsunamis are especially so for me. So to give you a couple of ideas here, we're going to use a sample of the Northridge earthquake in 1994. That was a magnitude 6.7, and it killed 57 people and injured 8,700 folks, caused $44 billion in damage in 1994 dollars, which is a lot of money, right? But this earthquake, what it's kind of famous for is it happened very near, only 5 years after Loma Prieta. And this is where California said, man, we better get our behinds in gear. Now that we know that we're an earthquake prone country, what can we do to make sure we don't crush people? And what really gets people talking, unfortunately, is how do we save our investments? How do we save transportation and bridges and infrastructure and things like that? People should be number one on the list. And I think for most scientists that is, but as we know, the way the world works sometimes, money speaks as well. So these were the impetus for better seismic networks and early warning systems. That's what this earthquake did. And what I want to show you is how the ground shaking and structural damage can be a major hazard here. All right, so the ground shaking in Northridge, it toppled over their brand new parking structure, but the big thing it really did was destroy several chunks of the 405 freeway, which if you're familiar with Los Angeles, it's kind of down by like where the Getty Art Museum is and stuff. And you know, the shaking hit the right period and it caused these to start shearing and swaying back and forth, and boom, multiple overpasses and stuff crumbled. And so after this, they made new bills, and they found ways to wrap carbon fiber skins around a lot of our concrete piers and stuff like that. So hopefully the next time it comes, it'll be much stronger and more resilient to this kind of shaking and breaking. They've re-engineered and made things more earthquake safe. But can you imagine being these folks on the highway in the middle of the night? That's when this thing hit, and then all of a sudden, and the road in back of you and the road in front of you just completely collapse. It's like a movie, right? I mean, just totally intense. And the apartment complexes, boom, they just totally smashed and collapsed and fell down. And this was some of the results of the car parks. Nobody was in here, it was late at night. But these were formerly like car parks, carports, you know, where some apartment complexes, even in Turlock, they have like those thin metal poles that hold up the entire building. Well, if they shake big enough, they can cause it to collapse. The metal pole can shake and give out, and everything else on top then collapses on top. And that's what we see here. So because of this, I'm going to show you some really cool ways we can engineer around this in just a few minutes. So that ground shaking and the period at which it was shaking was responsible for a lot of this structural damage here. And so these videos I'm going to show you, not too many folks were injured in these videos, and the building over here I'm going to tell you was not occupied at the time. But this is from the Mexico City earthquake 2 years ago. And I just want to show you some of the structural damages and effects of what happens during a big earthquake like this. You can see the building swaying back and forth, and it was covered in like a plaster type thing. And that plaster, you can see, was falling off the wall. So not only is it structural damage from shaking, but if you're someone underneath that building and all that plaster is falling off, that's going to be a problem. And Mexico was great. They've had an earthquake early warning system since the I think it was like mid 2015 or 14, somewhere in that neighborhood, maybe 2016. So they've had an earthquake early warning system longer than California and the West Coast of the US. The idea here with those earthquake early warnings is you want people to drop cover and hold on, especially if they're in like modern buildings. So all the buildings we're in California pretty much are the big ones, and they're newer, are earthquake safe, and we want to drop cover and hold on. And we never want to run outside during an earthquake, because this is what can happen. And I just want you to watch the two buildings too, how they're swaying. Buildings are literally clapping together, and you can hear the glass falling from these windows 5 or 6 stories up, huge panes of broken glass just raining down. And then people decide to run out, you know. So I'm not criticizing them in the moment, because when people are under stress, you know, maybe you do things that you just normally wouldn't think you would do. But that's why we try to have the great shakeout in these trainings, so that when an earthquake happens, you know to drop cover and hold on, so that you don't by all this falling glass, right? So we just have to assume in California and stuff that all of our buildings are going to withstand most any earthquake, and that a building is not going to collapse. And even if it did, which it shouldn't, but if you're dropping and covering and holding on, you have a much better chance of surviving and kind of finding a space that'll be fine. So check out what happens to this when the resonant frequencies of this building kind of get matched with the frequencies of the earthquake waves. Oh, what the heck? Sorry. And so remember, nobody was in this one, but you can see the building kind of swaying back and forth. It's an old brick building. And then the the whole thing just boom collapsed. And this was a really big problem in Mexico City in the 1985 earthquake, where they had kind of these medium-sized buildings like this matched the frequency of the earthquake waves going through the soils, and a lot of them collapsed. And so that one survived 1985, but I think it was still deemed like unsafe, so it wasn't occupied. And then this earthquake is what brought it down. So people couldn't be in it, but they thought, well, it's at least a good place to put like cell towers and things. But it didn't last too long. So that brings me to, what is this earthquakes and what is this resonance? What is this whole building stuff I'm telling you about? Well, I'll show you a quick little clip here. And
to understand the resonance of buildings during earthquakes, we will look
this guy
at
talks
other
into the
resonance
microphone
systems.
pretty.
The natural frequency of a swing makes it easy to maintain the motion using
Yes.
little energy.
I'm gonna.
A prolonged wind swung the bridge on
All right.
particularly when they hit broad.
So I'm going to show you the difference of what these resonant frequencies are. So when we talk about the periods of the wave, it's how many wavelengths go by in any given second. But so check this out. When we have waves that have smaller amplitudes and kind of go through quickly, watch what happens to the small boat versus the big boat.
Broadside can initiate rolling behavior.
So these are just ocean waves, not earthquake waves, but we're gonna use this as a model to compare to big buildings here, okay?
The smaller boat is affected by short period low amplitude waves that slap against the ocean liner with no effect. Small boats, on the other hand, will ride up and over long period high amplitude waves as the larger boats begin a long, slow rock.
So when it, doggone it.
A resonant period high amplitude waves.
So what I'm trying to show you here is short period means the waves are coming through much quicker. And if it's a lower amplitude, that means the heights of the waves are much smaller. So short wave, or basically lower periods or shorter distances between wavelengths, and smaller, squattier wavelengths, they do to buildings like they do to boats. If it's a small building, it's going to be more affected than a big building in those shorter period frequencies.
As a larger
If it's a
boats
big building,
begin a long, slow rock.
they'll do these big, slow, long rocks. And this is what happens exactly in earthquakes. The big, tall skyscrapers, they have larger periods. And so during an earthquake, if you're on one of those upper floors, you will maybe shake backwards and forwards, upwards of 2 or 3 feet up on the top as it just keeps swaying, kind of like a pendulum going back and forth. We can engineer for that so that it shouldn't be damaging or anything, but it's just something to think about.
Now, let's look at how buildings are affected by earthquake-induced seismic waves. All buildings have a natural period, or resonance, which is a number of seconds it takes for the building to naturally vibrate back and forth.
Yeah, oh man. So that resonance then is, like I said, it's the period that it takes for the building, or not like they said, the period it takes for the building to shake and go back and forth. So I want to show you how this affects the buildings when the earth.
All buildings of 1 or 2 stories resonate naturally at much less than 1 second periods. As 1 second period will affect buildings of about 10 stories. For example, a 30-story building resonates at a period of 3 seconds, and a 50-story building resonates at a period of 5 seconds.
So it's kind of interesting to think about. For every 10 stories you go up, it takes a whole nother second for the building to go back and forth 1 time. All right. So the resonant frequency is basically the time it takes to go back and forth. Small buildings takes less than a second because it's shorter, right? There's less distance to travel. It takes about 1 second for a 10-story building here. So
During
there's
the
kind of another
1985 Mexico City earthquake, the
Yes.
ground beneath the city resonated with a 2-second period for over a minute. Thus, medium-height buildings with similar natural periods suffered the most damage, while short, old, weak stone buildings and skyscrapers were relatively undamaged.
So it had to do with the size of the seismic waves going through here. And now because they know in Mexico City that the ground that they're built on kind of makes these low frequency, kind of high amplitude waves, like the medium periods, they build buildings that can withstand that type of shaking, right? So that's kind of the big thing to think about. And here's another way of modeling it. And if we were in person, I'd show you a similar.
Horizontal down motion. A tall building will respond to very slow or low frequency oscillations of the ground.
Oscillation just
So
means
if I move the
vibration.
base slowly back and forth, I can get the tall building to oscillate, where the intermediate and short buildings are not moving. If I move it more briskly, I can dial in the rate of horizontal oscillation so that I move the center building, the intermediate height building, and the short and the tall ones are barely moving. To get the short building to oscillate, you need to move the base very briskly back and forth and dial in to the natural frequency of the short building, and we can see that the intermediate and tall buildings are barely moving.
And so that's kind of what happened in Haiti. It was a shorter period, lower amplitude wave that really rocked all those buildings in Haiti. So how can we design for that? Well, there are literally universities that study this across the world. They build huge, gigantic shake tables that you can build full-size structures on, and then they shake it and move it and program it just like a real earthquake would do. So they build a structure and they see how it reacts. Unreinforced concrete, and you can see it just took a couple of little shakes there, and then boom, everything collapsed down. That's kind of like what happened to the parking structures and stuff in Northridge. And the whole building's a loss because it's totally unsupported. Versus building out of wood, things that are more flexible or things that have reinforcement in them, as opposed to like bricks or concrete with no reinforcement. Check out this. And you can see the people in that window for scale over there. And then imagine being able to build a shake table that simulates all these earthquakes like that. This is a full-size apartment complex that they built and they shook to see what it was like. And you're like, okay, that doesn't look like much, but what happens if we go inside to see? You'll see here. This is that same earthquake, but from inside. And so they test it and they'll see, you know, where the cracks were and stuff like that. But literally the thing that helps build this is it's made out of wood. The wood can flex, and they put special like metal straps that help hold the wood together in special ways so that it doesn't shift off and fall apart and break. So we can totally build safer houses and retrofit ones that aren't safe right now. So if you ever get a chance to go to Southern California, like all the parking garages, especially if they're kind of older parking garages, they have all these amazing, what they call buckling restraint braces on them. And they're like giant shock absorbers for the building. So when the building starts swaying, these absorb some of the shock and then push back a little bit. And at the end of the earthquake, these things will totally be destroyed, but the building is still standing, and then they'll just come replace these and put new like shock absorbers in or buckling restraint braces, and things will be fine. In LA and Oakland and Berkeley and all these cities near the faults, and even in places like Turlock too, one of the things that is happening is, mute this, but I showed you earlier those garages like this, that's carports. This is what can shear and buckle and collapse. And so now there's new state laws that say, hey, you can't have this anymore. You have to come fix this. And so the way they fix it is just like what I'm about to show you, but I'm going to make it go faster so you can see in double time here. Basically, they cut out the concrete, they dig a hole. And then once they dig the hole, they put in new pilings, I-beams and rebar and stuff like that. They keep the house kind of supported while they're putting it in. And then they pour new concrete with these new I-bars that, these new I-beams, I should say, that then are better able to support and bend and sway and sustain the loads when the earthquake happens. So, you know, it's kind of expensive, but it's a lot cheaper than having to build a whole entire complex. And the more important thing is nobody's going to die when this happens, right? Nobody's going to get crushed by a building. And that's the most important thing to think about here. So we can retrofit those. That's what we can do. In Turlock, like this is one of the things that a lot of folks always ask, like in the Central Valley, what are the things that we need to be most worried about? And for us, since we're like 45 miles away from the major faults, we could see some pretty good shaking during an earthquake, but it's not going to be like we're just right on top of the fault. So I would say, we could see like an intensity of a 7, perhaps maybe an intensity 8 in worst case scenario, as the waves roll through our sediments, which kind of amplify things. So for us in Turlock, if you live in a new house, you should be fine. If you have a concrete, we call it concrete foundation, you should be fine. But for me, I live in a house that was built in the 1930s, and it has like a basement thing, and literally the house is just kind of set on concrete. And so if there is a big enough earthquake, it could literally shift off the foundation. And if it does that, then my house is not going to be able to be lived in. So what we're doing is it just costs us a few $100s, which compared to the house is not that bad, a few $100s to go put bolts and literally bolt the house down to the foundation. In the past, they just built it there and the weight is enough to keep it on. But by putting these simple little bolts on, it literally prevents things from flying off. And, it's pretty cheap. And even if you don't own a house, if you rent a house or something like that, you can ask if it's an older house, ask if any retrofits have been done to, maintain its integrity in an earthquake so that you can stay safe. And this is all the stuff that's happening in the Bay Area. It's a law. Landlords and stuff have to do this. Not everybody's holding up to the law. It costs a little bit of money up front for sure. And some people don't want to pay that. But for the most part, a lot of folks are getting up to code and making sure this happens, because not only is it the right thing to do, but it's the law, and they could get fined pretty heavily if they don't fix it pretty soon. Because we are going to have a large earthquake at some point in our lives again in California. I can guarantee it. In the next 30 years or so, I guarantee we'll probably have at least one magnitude 7 or greater quake somewhere in a near populated area, and we need to be ready for it. So that was the earthquake hazards. That was the ground ruptures, and that was the structural damage. Sorry. Now we're looking at surface ruptures and ground ruptures, and basically what these are is literally what it sounds like. It's where the ground ruptures. It's all right on the fault. And so this case was a fault in New Zealand a few years ago, kind of on a little bit of a reverse fault here that uplifted the head wall. So that's what you see here, and that's what you see over here on the coast. It literally lifted up some of the ocean surface as well, and stranded it out of the ocean. So it's not just low tide, it's that everything kind of popped up too. You can see on the other side of the fault, it's still kind of normal and what it looked like before the side of the ocean got uplifted. But look, if you building a house or railroad tracks or cars, roads and things across that, they're going to be completely sheared in half, and that would be bad. So surface rupture is something we want to look out for. We can map it. We know where it exists now. And it turns out that a lot of hospitals and stuff down in Southern California, hospitals and schools for some reason happen to be disproportionately built very near faults, and we're almost right on top of faults, which is not good. So we're trying to figure out ways of how to handle that moving forward here. But surface rupture, that's basically if it busts underneath, you're not going to be doing well. So how do you prevent this? What's a way to engineer against that is find the faults and don't put a house that spans across a fault, or don't put a building that goes across a fault. Just stay away from it. And that's kind of the big thing to do. And so if you can imagine like a large surface rupture, if that happened this is a theoretical magnitude 7 scenario along the Hayward Fault by Oakland and Berkeley. And you can see that the shaking is exaggerated 1,000 times on this map here. So it wouldn't really shake quite like the jello you see here, but the intensity levels of shaking would be massive. And pretty much anything that's built on the fault here is going to sustain like some pretty significant damages. So that's what we're talking about with the surface rupture. It's like literally the ground busting up underneath it. So remember, the other thing here is It's not like the movies where the ground is going to open up and swallow things. It just shifts and will structurally compromise things as it shifts. It's not going to leave a chasm that the rock has to fly a helicopter across or anything like that. Okay, so that's a surface rupture. The next one is liquefaction, and I swear this is going to look like it's science fiction, but it's totally real. And what you're going to see in this bin, in this model version of it, is a box of sand. And in that box of sand, there's also been water that's been poured into it. But, you know, sand is porous, so the water will kind of sink down to the bottom. But if you start vibrating that sand, the water will start vibrating as well, and it will actually force its way up between the particles of sand and push the particles of sand apart and make it so the sand doesn't have the ability to stay strong anymore. And this is what happens. So these are weighted models of a house and a two-story house, a small house, and then just a weight. So watch what happens when they start vibrating this table, like if an earthquake were to happen. And we're going to see something called liquefaction here. So this is pretty amazing. All right. There we go. I guess they don't have the good sound effects, but you can see it starts wiggling and jiggling. You can see the water coming to the surface. And because that water works its way up and causes the pore pressure to decrease, the ground loses its structural integrity, and everything that was built on top of that ground, it could be completely solid and it didn't bend and break in the earthquake, but it's going to sink in like quicksand, all right, which is pretty nuts and pretty crazy to think about. So here's shows another reason why of how the poorly consolidated sediment and even the water saturated stuff can be affected by these surface waves moving through. Oops, let me see here.
The motion of similar buildings on different bedrock will be exaggerated to show the arrival of compressive P, shearing S, and rolling surface waves from a regional earthquake. 3 consecutive.
So by the way, this is one of the things on the sketch notes too, right? How do the different waves affect different types of rocks and things? Here's
Seismograms will show the changing frequency and amplitude resulting from the change in rock type. The initial P wave arrives with a compressive bump and rarely causes much damage. The slower shearing S wave introduces a side-to-side motion.
So I just want you to watch these houses and also watch the seismograms here compared. Look at the amplitudes, I guess, of how big the waves are as it goes through, and watch the houses too.
That can throw loose objects to the floor and may crack walls.
Right, so you can see in the solid bedrock, the S waves pass through very small amplitude, medium-sized amplitude, much higher amplitude in the water-saturated sediments and sand and mud.
The rolling surface waves are the most damaging in unconsolidated sediment. As surface waves enter the sedimentary layer, they slow down and increase in size, causing buildings to roll. If not engineered for the motion, they can crack and tumble. But even a well-engineered building can sink during the shaking and liquefaction of underlying wet sediment.
So here's the thing to take a look at. You'll notice those surface waves still in the solid bedrock, very low amplitude. You get into the more loosely consolidated sediment, kind of like what we live on in the Central Valley, and it's going to amplify those waves a little bit. It slows them down, and the amplitude goes up. They get amplified, they get higher. And when it gets to the water, my goodness, look at that. They slow way down and the amplitude goes way up. So the shaking is much, much higher, but it's all the same earthquake wave. It's all from the same earthquake. This is why you can have varying intensities. So solid bedrock, you're going to be pretty good to go. Poorly consolidated stuff, a little shakier, right? And then definitely the water saturated stuff is going to lead to some liquefaction. So like here's, oops, somebody had a chat, sorry. What part of the sketch notes of this? So that would be, let me show you here if I can get there. The seismic waves and amplitudes, it's this part right here where it talks about what type of ground and soil will the seismic waves have the greatest amplitude going through, greatest shaking, stuff like that. So this is the area that I'm talking about there. All right. So tallest, greatest waves generally going to be in those muds and saturated water, logged sand and mud and things like that. Okay. So that liquefaction then, to just kind of put some words on all of the things I've been saying, is causes sediments and loose particles to act like a liquid. The buildings sink, and we can reduce the threat of liquefaction by testing the soils before we build on it. So we don't want to build on areas that are subject to liquefaction, or if they are, like in San Francisco, what you can do is drill down through the loose mud and fill in all the way down to bedrock, fill in like concrete and stuff like that, all the way down to the bedrock, so that it's on something more solid and it won't sink when that happens. And so liquefaction totally happened in the 1906 earthquake. And you can see how the sediments kind of come through. This is just another good model to show what's happening under the surface here. And then I got to show you some really cool stuff. So the load just means the pressure of the ground pushing down. All right. And so when you have the liquefaction, it vibrates the water can squeeze up, reduce the pore pressure, and cause liquefaction like this here. So pretty impressive. And here's some liquefaction after the 1906 earthquake. And let me tell you, I have some way better ones than this too that happened in New Zealand, I think in 2013. I just kind of forget all of the dates these days. But here's some really great video of liquefaction in Japan from 2011 after the magnitude 9 earthquake. So this is after the major shaking, but you still have some of the surface waves going through. And what's interesting to note here is in this part of Japan, let me go, gosh darn it. Let me go to Google Maps or Google Earth here really fast, just to show you, because you need to see the context here. In Japan, right, it's a very highly densely populated country, and especially near Tokyo, they were running out of land. So one of the solutions they came up with is to mine parts of the mountains that are nearby. And they would take that dirt and rock and fill in the bay and basically make islands in the bay to build on top of. So we'll fly into here. And you'll see around the bay here, all these like not triangular, but polygonal like things like ports and stuff like that are there. All of this, if it's a polygon, if it's a land surface that looks like this was all human made, added in there, dumped in there, built on top of rocks that were mined from other mountains and stuff nearby. So because of that, it's literally soil or dirt that has water seeping into it from the ocean and from the bay that's here. So the soils here, even though they're nice and compact, they're still can be pretty saturated underneath deep down. So if you have an earthquake that goes through this area, it's going to jiggle those, and those sediments are going to get a little loose here, which you'll see right now. And this is a real honest to goodness video. It's a pretty amazing thing to see, but it's liquefaction in action, I guess. Oh, that's my cat. Sorry. So watch the ground here. So can you imagine being in an earthquake and all of a sudden, you're just seeing parts of the ground and break and shift like this? You can see the frequency is pretty long, right? So it's a low frequency kind of, it's a long time for those waves to kind of go back and forth here. It doesn't look like much, but if you fast forward just a few seconds here, this is what happens. It's not from a broken water main or anything like that. It's just all of that resonant frequency mashing together the water underneath in the soils, and it's squeezing the water up. And as it squeezes the water up, it causes the ground to start losing its stability. So that's the first part. But if you notice, it starts happening everywhere. So that's why they're running away. So this is kind of like at the start of a horror movie or something, it seems like. And you'll see every time the waves come through and cause the human-made islands to kind of bump into each other, it squeezes the water up and out between the cracks. And this is what liquefaction is. It brings up sediments and things with it. It's not clear water, it's bringing up the mud and the clay and the junk that was underneath it. Isn't that crazy? So like, it was hard to tell students like what that was looking like. Oh yeah, no problem. Ariel, no problem. So, I mean, it's pretty amazing to see what that looks like in person, because before we had all the cell phone videos and stuff like that, it was just super hard to describe like what the ground was doing. And this is exactly what happened underneath the ground, underneath the I-80 bridge down in 1989 in the Loma Prieta quake. So even though this was 45 miles or 50 miles from the epicenter of the earthquake, because the highway bridge here was built across soft mud, the waves amplified and that whole entire bridge collapsed. It was a double-decker freeway, and the top layer collapsed down onto the first layer, and that's what killed most of the people in the Loma Prieta earthquake, because it was right during rush hour, 5 o'clock in the afternoon, a little after 5 o'clock. You know, the World Series is going on and people were trying to get to the Bay Bridge, and that's what happened, and it collapsed. Because even though the road itself was built pretty sturdily, the ground underneath was not solid, and they didn't build enough connection down to the bottom to make sure it didn't wiggle during this earthquake. So what does that matter to us? Well, there are liquefaction maps. The USGS has the map, and I'll show you the interactive version of it here in just a minute. And you can figure out and see where the risk of liquefaction is very high or not very high in California. So anywhere in the Bay Area, there's a lot of landfill in there as well that they've built houses on and stuff. San Ramon, San Rafael, places like that. All of those areas are built on landfill in the Bay, and they have a very high susceptibility rate of liquefaction. And I would say in the Central Valley here, we probably don't have a huge risk of liquefaction, but we do have a high risk of our soils kind of amplifying those waves and making it not so great. So here's some of the results in 1989 of those sand boils after the water squeezed up. So if you imagine it squeezing up like it did in Japan, bringing up all these soils, that's what was happening here as proof that the ground was liquefying. And this was a field over in like Salinas or something like that. And as it turned out, one of my students from a long time ago was visiting her grandma in Mexicali in 2010 when the big Mexicali earthquake happened down there, and just south of Mexicali, but she was in Mexicali, and this was her grandma's yard where that earthquake caused liquefaction to happen in her grandma's backyard and brought in about 6 or 7 inches of sediment and dirt that squeezed up in what we call sand boils from that liquefaction process, which was kind of interesting. So now I know somebody who's seen it in person. But I think the most amazing things I've ever seen with liquefaction outside of those Japan videos was in Christchurch in 2011, the 6.3 quake. This was a paved road, man. And it liquefied so badly, it swallowed cars and trucks. And I mean, so imagine how much of like jello and quicksand that thing had to have been, where the whole road gets succumbed and then the car sinks in like that. And then the earthquake stops shaking. The water, there's no more pressure on the pores, so the water sinks down and all the dirt that's there just kind of fills in and it's completely solid. So, you know, I don't know the aftermath. I'm assuming they could probably dig some of it out. I don't think the car would ever be drivable again with all that junk in the engine and things. But just mind-boggling, right? I mean, it's like a thing of science fiction, but liquefaction can definitely happen. And it happened in the Kyoto earthquake in Japan in the mid-90s, where they had really well-designed buildings that just they didn't collapse, but they sank and got had to tear them down because liquefaction ate them up. So that's kind of the liquefaction part. Then the other one is landslides. And next week, we're going to be looking at more mass movements and landslides in depth and in detail. But basically what happens here is earthquakes shake loose the rocks from soils that are on steeply sloping areas, and gravity brings them downhill. And so that can obviously destroy vegetation and structures and people if you live there. So kind of the way to reduce this from having any effects on people is just maybe don't build houses right at the base of a cliff or a steep slope or things like that. Some areas it's hard to avoid if it's a kind of a mountainous and hilly region, but especially if it's made of loose sediments or not very strong sedimentary rock, That's a way to avoid that. So here's this is kind of a funny dude bro appreciation of some spring breakers back in 2010 experiencing the Mexicali earthquake on their way home from spring break, right? So it happened on Easter.
Wow. Oh my
Holy
God.
shit.
That was
That was a bad
gnarly.
word, I forgot.
No,
that was really scary.
You should call your dad. I wonder if the house is okay.
Oh my.
Yeah, I couldn't figure out if the road was messed up, and then I realized other
I
cars
thought
were
we
doing
had
it
a
too.
flat,
Yeah,
and then I'm looking over there, and it's
That was really
that was
weird.
intense.
Yeah, see, they know the Mercalli scale is intense, right? So they're out in the middle of the desert. I mean, this, if you're going to experience a really big earthquake, this is the best place in the world to ever have that happen, because nothing can fall on you. You're not going to die or anything like that. So the road was shaking so bad, they were right next to the epicenter, so they had to pull over. But all of the dust is from landslides that were sliding down the canyons of the mountains. And the other thing I just kind of want to mention here, oops, not him, but these guys look like total SoCal people, right? What I also want to mention is when you see mountains that kind of have these triangular shapes right next to a flat valley, this is your fault right here. This is the fault, and this is your head wall, and this is the foot wall. And so this whole line of mountains here exists because there's a giant fault that runs right along through here, and the valley is slowly sinking down after every earthquake, and the mountains are kind of popping up a little bit. So this is our head walls, and this is our foot wall sliding down on these normal faults. So if you're ever driving down a road, especially in Nevada and stuff, and you see these long lines of mountains where it's valley and all of a sudden mountains pop up, there's a fault there. Death Valley is another good place to see that. So the landslides, kind of earthquake induced landslides closer to home. There was a 5.8 back in June of 2020. Luckily, it was COVID, because this is the most popular, one of the most popular hiking trails in all of California to go to Mount Whitney. People have to sign up for years in advance to get permits to climb it and stuff. And there's usually hundreds of people camped in these campgrounds, but because of COVID, no one was there. And this magnitude 5.8 earthquake that happened about 25 miles away caused a really huge rock fall that came down. And this is the campground. All this stuff that you're seeing here was the campground that everybody used to camp at. And if people would have been there, it would have wiped out, hundreds of people. So that was kind of the good news of COVID, I guess, and keeping people away was there just weren't nearly as many people there as there could have been. So that's kind of a silver lining. And after 1989, right? I keep showing you 1989 stuff because this is what happens. There's $1 million homes right on a cliff next to the Pacific Ocean. The cliff is made of sediments. It's a steep cliff, and you give it a little shake, down it went, right? So if it were me, I wouldn't invest lots of money on a lot of house right next to the cliff of an ocean. But, I guess people have lots of different kinds of money. I don't have that kind of money. And the earthquakes also caused landslides across Highway 17, going to between Santa Cruz. That's the highway between Gilroy and Santa Cruz, going over that way. And it took a while for all this to get cleared off and to engineer to make it safe. So one of the things that you can look at is that interactive earthquake map. That's the part on your sketch notes that is right down in here, this little link. And when it opens up, you'll notice they've mostly concentrated on highly populated Southern California areas, a little bit of Bakersfield, because there's a fault down there that's pretty big, and also the Bay Area up here, and a few places like up by Tahoe and things like that as well. So you can use this if you choose to live in one of these areas in this hypothetical thing, or in real life, you want to live in these areas, you can zoom in and interactively click on these things. Like if I lived in Fremont or this area of Newark, I can click on that. Oh, it's a liquefaction zone. And so you can get the report link and say, oh, this is a pretty high area of risk of liquefaction. Or if you click on the blue areas, these are your landslide zones. So these are the hills that you're at risk of landslides. And our state geological department or survey is putting these out so people can have the information. Realtors can have that information. Builders can have that information so that people can stay as safe as possible and protect their investments if they were to build a house somewhere. And then if it's a yellow zone, that's the fault zone. And that's basically a no-no. You don't want to build anything on that because that's where you can get your surface ruptures, right? That can really jack some things up. So, but if you take a look, if we have, here's the San Andreas fault, here's the Hayward fault over here. A magnitude 7 on either of those faults, and it's going to be liquefaction city for a lot of places here, San Francisco Airport and things like that. So there's ways to engineer around it. There's ways to make it better, and we're trying. And we've invested over $80 billion in the Bay Area in the last few years to make sure that it's better. So it's not going to be a complete catastrophe, but it still could be pretty bad if it happens right underneath the city. All right. And we just got to be prepared for it. That's kind of the big thing here, is preparedness. And so when you're thinking about those, you can use that map in your sketch notes to figure out what type of hazard you live next to. Another hazard that a lot of folks don't remember or don't think about too much, and then we'll end on tsunamis here pretty quickly, is fire. And when you have an earthquake and it breaks a gas line or it breaks water lines, then you can't put out a fire. That allows fire to spread pretty rapidly. That's what happened in the 1906 earthquake in San Francisco. Broken water lines prevented them from putting fires out. So 2/3 of the city burned to the ground in 1906. Modern times, we have the broken natural gas lines and things. And if there's gas spraying out and you have a downed sparking wire and hits that gas line, maybe it blows up and creates a fire. And that's kind of what happened here in Mexico City. This is also another Mexico City video here. You can see a gas burning, something sparked it and then got down into the kind of the main line, and boom, explosion. And not only does it explode, but it sends pieces of fiery things into other buildings, which can catch on fire, which is not a good thing to have happen, right? So we can reduce this type of damage by having better building codes, strapping all of our water heaters and water lines so they don't break and sway. And now the most important advancement we've had in the last 20, 30 years are these automatic shutoff lines on gas lines and water lines. So if it senses and detects enough motion, they just clamp off and it doesn't open up, and that prevents it. So if it does break, no water will be lost or anything like that. Okay. And so here's some pictures of that 1906 fire in San Francisco. Like I said, 2/3 of the city burned to the ground. And then guess what they did with all that rubble and garbage? They trucked it off and dumped it in San Francisco Bay and said, this is where we're going to dump it. It's the Bay. And once they did that, they put some dirt on top of it and said, oh, hey, we just made some new land. We'll build new houses here and we'll call it the Marina District. And so the Marina District was literally built on top of the unconsolidated rubble from the destroyed remnants of the 1906 earthquake. And wouldn't you know it, in 1989, that Loma Prieta quake, because of the soil was so poor, because it was built on the old garbage of the 1906 earthquake, these were the houses that were hardest hit and had some gas line ruptures and caused some fires too. So that's the fires, and that's how we can prevent against those. And we're going to end with tsunamis. And if you're a beach person or you like going to the beach, this is kind of important information to know of how to stay safe. I can tell you this right now, we will never experience a tsunami in Turlock, right? We are way too far away from the ocean. And also, it would be really hard to experience a tsunami inside San Francisco Bay even. I guess there could be some really weird outside things that would cause one, but for the most part, tsunami waves are not going to travel very well through San Francisco and the Golden Gate Bridge and things like that. So we're not going to see a tsunami here. But if you live on the coast, on the actual coast, outside of the bay and on where the Pacific Ocean meets the land of California, that's where we could see them. So how do tsunamis created? Well, there's a lot of different ways, but earthquake related, all right, is the main one that we're going to be taking a look at. And landslides can also do it too. But we're going to be looking at this one right here, where reverse faults at subduction zones build up stress over time. And when they rupture and the head wall goes flying up in this earthquake, it can lift the ocean floor above it. So here's what that looks like.
Subduction zone megathrust earthquakes, the most powerful earthquakes, can produce tsunamis through a variety of structures that are missed by simple models. The basic model shows rock above the convergent plate boundary being compressed and bent as it stores elastic energy. Once friction is overcome, the overriding plate slides abruptly up the fault, causing the leading edge to heave seawater upward, generating a tsunami.
So this would be at a subduction zone, right? Where you have an oceanic plate subducting underneath either another oceanic plate or a continental plate or something like that. And as that tries to pull down, right, because of gravity, it loads all the stuff above it. And when it ruptures, it flings that water up on top. So those waves, what's kind of crazy is those waves in the water can travel at over 400 miles an hour. And in some cases, I think in some cases, excuse me, it might be even a little bit higher than that. But they're kind of shallow waves, right? They don't go all the way down to the surface. So if you were out in the middle of the ocean, you wouldn't feel a tsunami happen. I mean, you might hear it or something like that, but you wouldn't feel the tsunami out in the middle of the ocean. In order to feel the tsunami, we'll talk about this too when we get into the ocean processes towards the end of the year. But in order to feel the tsunami, it kind of builds up and slows up when it gets to the shore. And that's where you start being able to feel it and see it, all right? If you were in a boat or if you're on the shore. So let me show you how that happens, all right? So the tsunamis, just like you saw in that video, they're the waves created by submarine earthquakes. So that's the first thing. You have to have earthquakes that happen under the water in order to make a tsunami, all right? Most of the time. There's caveats here and there where, you know, you could create an earthquake that causes a landslide that falls off into the water, which makes a big splash. But generally the big tsunamis when we think of tsunamis like in Japan and Indonesia, this is how they're created, right? Underwater reverse faults. So the plate pushes the water on top of it, and that creates these walls of water, these waves that go out that then build up into walls of water as it hits the surface of the continents or whatever it bumps into, right? So take a look at this. This is that Japan earthquake in 2011. Look at the displacement here. The seafloor in parts of this area literally jumped up over 18 feet. And it did this, and here's 50 kilometers. So, you know, over a couple 100 kilometers worth of distance, raising the whole entire ocean floor up 18 feet for 200 miles. Think of how much water that uplifts all at once. And think of the energy that gets radiated out from there. And that's kind of what happened. And so we'll come back and I'll show you some other videos of what it looked like on shore in just a minute here. But if we're looking historically, before we had earthquake early warning systems and tsunami warning systems, you know, tsunamis could kind of come out of the blue. And in 1946 was a great example in Hilo, Hawaii. People went out to the beach because the water was starting to recede. This is what happens as tsunami waves come in. They literally pull water out from in front of it to build their waves higher. And people went down to the beach to sightsee, like, well, that's a really weird thing. Why is the beach, all of us, or the water disappearing from the beach and going way out? Where's it going? What's happening here? And the reason that happened is because there was an earthquake in Alaska. That was a magnitude 7.8. So the folks in Hawaii, they would never feel an earthquake from Alaska. But, you know, 12 hours later or so after that earthquake, those tsunami waves arrived in Hawaii, and the people that were down there unprepared, didn't know that a tsunami was coming, didn't have warning systems, got swept away, and 160 people were killed. And this is the tsunami coming over one of the seawalls there just before it rushes on shore, which was pretty tragic. We had a tsunami in 1964 from the huge Great Alaska earthquake in 1964. There is a 9.2 that caused a 21-foot tall tsunami in Crescent City in California, Northern California, right up there. And this kind of shows the waves, how they went out in different, I think these are hourly progressions or so, how many hours it took to get from here over to there, which is just kind of mind-blowing, right? People were asleep in the middle of the night, 10 deaths. They would have never felt an earthquake from Alaska. But here's this big sneaker 21-foot wave that comes in near people that live near sea level and just wipes away everything. And you're going to see a video here coming up where it's not just like a wave at the beach where it comes in and crashes and breaks and then it's done. No, it's a huge wall that just keeps pushing and pushing and pushing inland. So those tsunamis, the reason I mentioned those tsunamis in the US is because they really started setting the groundwork for us trying to say, hey, we need information so we can try to prevent these tsunami hazards from happening. So we started creating these DART. The DART stands for, what's it stand for? Deep Ocean Assessment and Reporting of Tsunamis. And they're basically these floating buoys out in the middle of the ocean, and they are connected, or they're anchored to the seafloor. And then they're connected to these pressure recorders down at the bottom. And if a tsunami goes by, it causes the water pressure to change. It'll send off a signal to this and it'll send that signal and pressure change to the buoy, and the buoy will communicate to a satellite, which then relays all the information to the middle of Hawaii, where our tsunami warning center is for the whole entire Pacific Ocean. Scientists will look at it and say, oh no, there's a tsunami. How much time do we have until it gets to all these other places? And so they'll send out these signals and call people and put out the warnings on the internet and give people a big warning. Now, you'll notice Indonesia and places like that, they didn't really have much of any earthquake early warning systems. And in 2004, they had a big tsunami and an earthquake and tsunami in Indonesia that just ended up killing over 200,000 people because they didn't have the earthquake early warning system. So here's kind of the before some of these places in Indonesia and the after the tsunami washed across it. And you can see in this little diagram here that the world's biggest quakes, like those big reverse thrust fault quakes, the magnitude 9s, they unleash those huge walls of water and they travel out, right? That's kind of the initial drop in the bucket, so to say, as those waves kind of spread out and keep racing across the ocean. Like I said, 480 miles an hour, somewhere in that neighborhood. But because those waves are shallow, they travel really fast. You wouldn't really feel them out in a boat. You wouldn't even notice it until it gets closer to shore. And once the seafloor starts shallowing up, the waves start slowing down on the bottom because there's more friction, and allows the waves on top that are going faster to kind of start building up and running over the top of it. And it builds these big, huge waves that then come ashore and push on. And this is what a tsunami actually looks like. It happened in the Japan quake in 2011. And this is the first time we've ever had like live video or footage of the tsunamis coming ashore. And it was just mind-boggling to watch live when it was happening. So this is the river that's normally flowing the other way. And now this is the first part of the tsunami starting to wash in. It just keeps pushing and pushing and pushing. Go on YouTube later, you can just Google Japan tsunami and find so many amazing pictures. But that was the first initial part. Now here comes the rest of the tsunami, and it went up the entire coast.
And it looks like the tsunami has engulfed several cities in Miyagi Prefecture.
I mean, it's just
live footage of Miyagi
mind-boggling here.
Has struck the area, obviously engulfing farms, homes.
And in this case, in this part, it was only 15, 20 feet deep or so. But there were places along the coast in Japan where, because of the way the surface of the seafloor was, the wave was over 80 feet tall, right? So it took these huge boats and like we're putting them 80 feet up on land and on over buildings that were able to withstand. And can you imagine driving around and all of a sudden here's this huge wall of water? I mean, you can see them starting to drive and go away here. But it was terrible. And Japan had built seawalls to prevent like upwards of 10 or 20 foot tall tsunamis, which is good and, you know, a little bit, but this was so much greater than anything they had designed for. And it just overwhelmed and overtopped. And in some cases went 6.5 miles inland, depending on, you know, how how shallow the valley slope was. And so it went in, and then right, all the water washing out takes all the debris out with it. One of the crazier stories was an old man was washed to sea from his house. He was able to stay on his roof, and they found him 10 miles out in the ocean a few days later, and was rescued, which was pretty intense. But the tsunami here, I think it was responsible somewhere around 10,000 deaths, somewhere in that neighborhood in Japan. And so that was with great engineering and with great warnings as well. It just happened so close to the shore that it took a lot of people by surprise. So what should you do to stay safe in a tsunami? All right, what should you do? Well, here's the first thing. If you're near the coast during an earthquake, obviously the first thing you should do is run uphill to higher ground. That's how you beat tsunamis. You go uphill, you go to places that are higher and taller than the water, right? And in California now, we have a lot of these tsunami evacuation zones and routes. Almost every California beach should have these now. You should be able to notice these, and the signs point you uphill and away from the ocean, okay? So look for those evacuation signs, follow those. I would say probably running is probably a better option than getting in your car and trying to leave, because you're going to be more nimble trying to get up and going to these places. Unless you physically can't do it, cars are going to clog the streets and people panic, and you'll be much more fleet of foot to get up hill faster than what a car can do stuck in traffic. All right. And so here's the other thing to remember, though. Most California earthquakes, because we have the strike slip fault along the San Andreas, they don't create these reverse faults with big, huge tsunamis. However, it's always best to play it safe. There was a weird tsunami that happened a few years ago, like 5 years ago in Indonesia, that happened on a strike slip fault that caused an underwater landslide that then created a tsunami that was kind of just really weird and unexpected. So you never know. And so anytime you feel an earthquake, just get away from the ocean to play it safe, right? That's the big thing to do. The tsunamis that affect California are normally caused by earthquakes thousands of miles away, or at least hundreds of miles away. Our nearest subduction zone quake that could produce tsunamis like this would be along the Cascadia subduction zone. So Oregon and Washington coastline is very capable of producing like a magnitude 9 earthquake. And that could produce a huge tsunami. And it did in the 1700s. We know for certain in the 1700s, and caused a tsunami that hit Japan pretty hard back then. And we have the historical writings from the Japanese historians and things to know the exact date that happened. And it's going to happen again at some point. Just who knows if it's our lifetime. But if you see the ocean go way out suddenly, go run to higher ground. That's another thing I was telling you about, how the ocean kind of draws back. And that's what killed so many people in Indonesia when the earthquake happened. There were so many tourists there, and not an oral tradition in history to know that when the waves go out, you go uphill. And so tourists just started flooding the beaches. And there's all these pictures that are just kind of too sad for me to show, of tourists on the beach, like, oh, scouring and picking up all these weird fish and things. Like, the ocean just disappeared. And then, in the background, you see this huge wall of water coming their way. And it just wiped out so many people. It was so tragic. So also, if you see the water, run uphill too. Which brings me to Santa Cruz, because that 2011 earthquake in Japan caused that tsunami that spanned the Pacific Ocean, and it reached California about 13 or 14 hours later. Those tsunami waves reached here, but because of the way because of the way the angle of the coastline was in California, we weren't as heavily affected by a huge tsunami, but in some cases it was like 3 feet tall, like in Santa Cruz. So what did Californians do? Oh, there's a tsunami, but do we evacuate? No, they ran down to the harbor to go take video of it. I would say if they were up higher, it would be safer, but I wouldn't be on this road or that bridge, to be honest with you. Here's what a 3 feet tsunami from Japan looks like when it comes ashore in California. And believe it or not, I think this caused like $10 million in damage or something to the the boats. It's a million, in the millions. I gotta remember. It's been a few years since I remember reading that one, but several $1 million damage came in and came out in some of these boat harbors here. There was a person in Eureka died. They went out in Humboldt County. They heard about the tsunami and they wanted to go experience nature, and they experienced it a little too hard, which was pretty terrible here. And so, yeah, that tsunami actually killed a person in California. So now, like I said, you'll see these tsunami evacuation signs in Hawaii. They look like these hexagons in California and Oregon and Washington. They're the round ones that you saw earlier. But you get above this and you should be safe in the worst case scenario. And in Hawaii and in California now too, we have these huge tsunami warning sirens. And you can hear them for miles and miles away. They are so loud. And if you hear those sirens, you get off the coast and you go up shore, all right, or go uphill. And luckily in California, most of our coasts go pretty steep, right? So you just get the heck out of there. And then this one quick other weird tsunami I want to mention here is Lake Tahoe has actually had a tsunami somewhere between 10 and 20,000 years ago from a landslide that occurred underneath the waters there. And that motion of broken land and landslide literally crossed the lake and caused a huge wave to go about 300 feet up on the other side, like a bathtub. So imagine pushing all the water out in the bathtub and then sloshing back in. That's why we have all these ripples on the eastern shores of Lake Tahoe here, is from the waves that sloshed up and then brought sediments back down in. But we can find all these really crazy pieces of stuff stranded high up 300 feet where above the lake of the lake surface. You're like, how did that get up there? And then they realized, oh my God, there was a tsunami. Once they were able to take a look at the bottom of the lake floor. And remember, Lake Tahoe sits in a whole bunch, it's called a graben, or a bunch of head walls. Normal faults have basically slid apart and extended Lake Tahoe, and that's where Lake Tahoe sits. So there are 5 major faults right in Tahoe, or right next to Tahoe itself, that have created the basin. And if there's a big earthquake there, it could create another landslide. And while it's very unlikely in our lifetimes or anything like that, it's just something that has happened in the past and be something to be aware about in the future. So if you feel an earthquake and you're by Lake Tahoe, don't chance it. Go uphill. All right. That's what I would say. And so we'll end with, I won't show you this because I want you guys to get out of here, but when you see movies like San Andreas and you see these major tsunamis, right? This is why you never want me to watch a movie like this with you guys, but right, total bunk. You're never going to get a huge giant tsunami this tall in San Francisco because we have the strike slip faults, and like 80 feet is a massively tall tsunami. And these things are hundreds of feet tall. So they're just way out of proportion to what could actually be produced. And, so just something to think about if you happen to watch San Andreas anytime soon. The mega tsunami is mega BS. And I'll end with the last thing here is on this slide. If you click on that link, there's 7 steps to earthquake safety for you and your family and how to make a home emergency earthquake kit. Please take it upon yourselves to take a look at this and get a couple gallons of water stored away, some first aid kits, an emergency radio. I'm not kidding you. Like, when an earthquake happens, we're gonna have to be able to fend for yourselves for a few days. I mean, power may be out, cell phone communications might be out. So if you have an emergency radio, you can listen to what's going on here. You can't count on cell phones or anything like that to keep us safe. So try to get some, canned provisions and things like that. If you can, have a go bag, have a plan. And this, if you go to this website, it'll help you and your family create an or roommates or whoever you live with, a 7-step earthquake safety plan in case there is an earthquake, right? And can't reach anyone. So I beg you, please go do it. I'm not assigning it, but it could be very useful for you in your life moving forward. All righty, so that's all I got, and we'll end it there today. And thanks for sticking in there, and thanks for being here on a Friday. And I hope you have a super great weekend. I hope you can go not have to work all the time or whatever. But and I hope this was kind of interesting to see how you stay safe in an earthquake here. And now you know, and knowing's half the battle, right? Yo, Joe. So that's all I got for tonight. I'll see y'all later, and see you next week. Have a good night.